the last section of chapter 1, and we're going to discuss inverse functions. So far we talked about functions. What is the function? Okay. As you remember, a function is a rule where we have two sets. Of course, we have set xy or dr instead of xy. Remember, we said for a function we said we have a set x and we have a set y, and then we said function f is a rule that corresponds to each x here, a y in set y, like this. This is a function. See? Now we talked about domain and range. So instead of x, y, may very well, instead of using x and y, maybe I can use domain and range. That's better. You see, so we have a domain of a function and a range of function, and a function is a rule. This is just a reminding from what we have studied so far. Is a rule that this assigns to each element x. This is x1, x2, x3, x4, x5. Each element x in a domain corresponds an element, let's say y1, y2, y3 in the range. Okay, so we have domain and range. Each element in domain has a unique element assigned to it in the range. Okay, so that's the definition of function. And in particular, it was allowed that two input values of x to have the same y value. Okay, so that was the definition of function. Now we're gonna look at a specific type of function that does not allow two different x's to have the same y. You see? So then, in other words, not only one x cannot have two different y's, one y cannot have two different x's either. Something like this. You see? If I have, let's say, 1, 2, 3, 4, 5, and then in this case I'm gonna have the same number of elements actually. See, x1 goes to y1, x goes to y2, x3 goes to y3, x4 goes to y4, and x5 goes to y5. You see, what is the difference between these two functions? Well, both of them are functions, of course. In this function, as you can see here, like these two guys have the same output. It's okay. It's a function. The same thing. These two have the same function, but here we don't allow that. Then the type of function we get, we call it a one-to-one function. Okay, so we have a function, then we're gonna make it one-to-one. So let's see actually how the definition goes. So let me, before I write the definition, let's see what it says here. You see, so that means that if x1 and x2 are different, like here, x1 and x2 are different, but their y's are the same, it's okay. It's a function. For here, x4 and x5 are the same, are different, but their y's is the same. But here it says no, if x1 and x2 are different, their y's must be different as well. So in other words, any two of these x values you choose that are different, their y value must be different. Okay, if that happens, then the function is called a one-to-one function. So let's see what the formal definition is. The formal definition is that a function f, so we have to start with the function, okay, is called a one-to-one function if and only if different x values x in the domain have different y values in the range. So that means if x1 is not equal to x2, neither are f of x1 and f of x2. This is the y value. So their y value are not the same either. Therefore, the contrapositive of that, if you want to say that differently, if their y's are equal, then the x's must be equal. So these are actually saying the same thing. Okay? So if x1 or if two x's are not equal, their y's are not equal either. If the y's are equal, then the x's must be equal. So these are basically the same concept. So that's what a one-to-one function is all about. Okay. So again, like if you go to this example here, you see these two are examples of functions. This is a function. This is a function, but this is not a function clearly. You see, because 1x goes to 2y, so this is not a function. Not a function. So we don't have to worry about being a one-to-one. So if a function is going to be a one-to-one, it has to be a function first. So like these two. This is not one-to-one. Of course, I'm going to use the notation. You see, 1, 2, 1. I'm going to write 1-1. So when I write 1-1, that means one-to-one. That's a shorthand note for one-to-one. So this is not one-to-one because this is 2-to-1. You see, these two going to same one. This is one-to-one. You see, every two different x's, they have different y's. So this is one-to-one. If you want to show something is one-to-one, then you have to show it in general. Like here, this is a linear function. This is a linear function. It turns out that all linear functions are one-to-one. Because if I start with x1 equal to x2, so let x1 to be equal to x2, then I'm going to show that f of x1 is also x1 not equal to x2. I want to show that their y's are different as well. So let x1 not equal to x2. Then what I would do, I multiply both sides by -3. If I multiply both sides by -3, 3x1 is not equal to -3x2 either. You see? And then I'm going to add 4 to both sides. So that means -3x1 plus 4 is not equal to -3x2 plus 4. Okay. But by definition, the left side is f of x1. The right side is f of x2, and they are different. So what I just did then, I proved that this function is one-to-one, because no matter what x values you choose which are different, x1 not equal to 2 in general, then the y values f of x1 is not equal to f of x2 either. So this is one-to-one. Of course, in a few minutes I'm going to show you a graphical method to determine whether a function is one-to-one or not. Okay, but before we get to that, we have to do it this way. This function, squaring function, f of x equal to x2 plus 1, is not one-to-one. So I say this function is not one-to-one. So if I want to show is not one-to-one, then I have to produce one counter example. In other words, I have to find two different x values that happen to have the same y values. Then that wouldn't make it one-to-one, makes it 2-to-1. There are a variety of examples. For example, let's choose x1 to be 1, x2 to be -1. If I choose x1 to be 1, what is f of 1? F of 1 is 1 squared plus 1 is 2. What is f of -1? F of -1 is -1 squared plus 1. But -1 squared is 1 plus 1, you still get 2. You see, I have 1 and negative 1. Both of them go to the same value 2. So this is not 1 to 1. This is a counter example. Of course, instead of choosing 1 and negative 1, I could choose 2 and negative 2, or 4 and negative 4. You see, so this is not 1 to 1, because this is one example that shows it's not 1 to 1. 1 and minus 1, they are different, but they have the same y. But here, it was different. I proved it here for a general situation. I started with not equal x values, whatever they are, because x1 and x2 are just symbols. They represent two different numbers, and then I showed that their y values are different as well. Okay. As I said, it's going to be a graphical technique which very easily shows why a function is 1 to 1 or not 1 to 1. Okay, so we get to that in just a minute. But before then, let me look at a couple examples which are given in a set of order pairs. How can we determine whether these are 1 to 1 functions? We have to do two things. First thing is to make sure there are functions, because if they are not functions, it wouldn't make any sense to show they are 1 to 1. They have to be functions. And then after we make sure they are functions, then we have to see if they are 1 to 1 functions. So let's see. Is this a function? Yes. You see, 2 is not repeated. 3 is not repeated. Negative 1, 4. So this is definitely a function. Is it 1 to 1? Well, if the first number is not repeated, is 1 to 1. But if the second number is not, if the first number is not repeated, is a function. Like here, you see, neither one of the first number is repeated. If the second number is not repeated, then it's 1 to 1. So you see, 2 here, 1 is not repeated at the second number. 0 is not repeated. 5 is not repeated. 7 is not repeated. Neither is 2 nor is 3. So the second numbers are not repeated. That means that if I choose any two first numbers which are different, they have this different y value. So this is a 1 to 1. This is a 1 to 1 function, since no second number or y value is repeated. Okay. In fact, if you draw the diagram goes like this. You see, 1 to 1, 1, 1, 1, 1, 1, and so on. Let me see if I can actually. Well, I'll do it for the next one. Let's see what the next one is. Is this a function? So let's see. 3 is not repeated. Neither is 2. 0 is not repeated. 7 is not repeated. 1 as the first numbers are not repeated. So definitely, clearly a function. But if you look at this 2 here, you see 2 and 1, they have the same second number. You see, 2, 1 and 1, 1. So that means this is 2, this is 1, and then both of them go to 1. So not 1 to 1. So the second number is repeated. When second number repeats, then it's not 1 to 1 anymore. So for a function, for something, for a relation, so let's just say this one more time. For a relation to be a function, first number must not be repeated. For a function to be a 1 to 1 function, the second number must not be repeated. Like here, the first number is not repeated, so it's a function. The second number is not repeated, so it's 1 to 1. Here, the first number is not repeated, a function, but the second number 1, you see, is repeated. That makes it not one-to-one. Okay, this is the next page. The question, as I advertised this question, how can we determine that a function whose graph is given is a one-to-one function or not? Well, the answer is given by the so-called horizontal line test. So what is that? Let me just show you on paper what this is all about. See, if I have a function that looks like, let's say, this, okay? Now the question is this. Clearly, this is a function. Why? Because it passes the vertical line test. Okay? Passes the vertical line test, so a function. Now the question is it a one-to-one function? Now if I draw a horizontal line, you see, anywhere, somewhere here, you see, I have this point and this point on the graph. They have the same y value. Let's call it y0. But if I go down on x-axis, I can call this one x1 and x2, and clearly x1 and x2 are different. x1 not equal to x2. You see, they are different numbers. But f of x1 is equal to f of x2, which is the same thing, equal to y0. y0 is f of both of them. This is f of x1. It is also f of x2. So this function is not one-to-one. So that gives us the tool we need. So if a function has a graph and its graph is intersected at more than one point by a horizontal line, then that function is not a one-to-one function. This is called a horizontal line test. If a horizontal line, if one, all you need is one. If one horizontal line you can find that crosses or intersects the graph at more than one point, then you can conclude that that function is not one-to-one. Of course, in this case, there are more than one line. I can draw this line. You see, I get two intersection points here, so I can do this. You see, so there are many horizontal lines that intersect at more than one point. So definitely, this function is not one-to-one. This is called the vertical line test. So let's read it. What it says: a function is one-to-one if and only if every horizontal line intersects the graph of the function at one point only. So based on this definition, this is not one-to-one. But if I draw something like this, you see, this is definitely a function because it passes the vertical line test. You see. But if I draw any horizontal line, you see, if I draw any horizontal line, I get one point, intersection point. Here, if I do horizontal line, I get more than one point. So what's the difference between these two? This is one-to-one, this is not one-to-one. You see? This is called the vertical line test. So a function is one-to-one if and only if every horizontal line that crosses the function, it will intersect it at one point only. At one point only. This means that two different x values in the domain, this means that no two x values, two different x values in the domain have the same y value. You see, if you choose two different x values, x1, x2, let's say, this x1, this x2, they're different. And then this one gives you this y value, this one gives you this y value. You see, the y values are different. If x's are different, the y are different. But here, these x's are different, but the y's are the same. So this is not 1 to 1, this is 1 to 1. So that's the essence of the horizontal line test. So based on this test, let's see which one of these graphs represent a 1 to 1 function. Clearly this is not 1 to 1, because if I draw this horizontal line right here, you see you get more than one intersection point. This is 1 to 3 to 1. 3 different x values have the same y value. Or even if I do it here, it would be 4 to 1. You see, if I do it here, you see I get 1, 2, 3, 4, 5 intersection points. So this is pretty bad as far as not 1 to 1-ness is concerned. But here, this one is 1 to 1, because if you draw any horizontal line, you see, intersect at 1 point. This particular horizontal line here does not intersect the graph. It goes on to infinity. They touch each other at infinity. So there is no intersection point right there. So we're safe. This one is 1 to 1, because if you draw any horizontal line, you see, you always get one intersection point. This is 1 to 1. If I draw horizontal line, you see, this is not a function. Because it passes the fails the vertical line test, so not a function. If it's not a function, you don't have to say whether it's 1 to 1 or not, because it's not a function. It has to be a function before it's 1 to 1. Okay? So you have your choices or your own technique to use to determine whether a function is 1 to 1. The easiest way is to use graphing technique. Okay? So like these examples, I want to know which one of these graphs are 1 to 1. I just go ahead and graph one at a time, and see. Let's do this function here. 3x plus 7. Negative 3x plus 7. My window is okay. So let's see. Yeah. Maybe make my window a little bit bigger. Make it zoom 6 to go to standard window. There we go. It's 1 to 1, because if I do any horizontal line test, you see, horizontal lines always intersect at 1 point. So I say 1 to 1 by graph. Horizontal line test. B, you want to do this one? Square root of 2x minus 1 there we go. That's your graph. Again, if I draw horizontal lines, if I draw any horizontal line, you get one intersection point. So here I would say by horizontal line test and graphing 1 to 1. Okay, check mark. It's okay. Let's do this one. test, you see, if I draw any horizontal line, it's similar to this one, you see, similar to this graph here, it's 1 to 1. This might be the same thing actually. I just changed the window, so if I change the window a little bit, let's see, if I change the window to, let's say, minus 4 to 4, and this one minus 5 to 5, just a bigger a little bit. I see them. Yeah. These vertical lines that I drew here, we're going to discuss these type of functions later. We call them rational functions. You see, these are so-called asymptotes. Okay, they don't intersect the graphs. You see, they meet the graph at infinity, so they don't have intersection point with graphs. Okay, and when you graph such function on your graphing calculator, it doesn't graph the asymptotes. So this the horizontal lines. If you draw horizontal lines, you get always one intersection point. So this is 1 to 1. Okay. Horizontal line, this, and graphing gives you 1 to 1. And this one, parenthesis, x plus 1 divided by parenthesis x to power 2 minus 4. Now, so let me use the same window to see how the graph looks like. Okay, well, maybe I should extend my x value a little bit more instead of 4, let's say 8. Okay, you see, if I draw a horizontal line right here, you see, if I draw a horizontal line right there, we could cut the graph at more than 2 points, right here. Down here, if I draw a horizontal line right down here, I get 2 intersection points. So, by horizontal line test, in graphing, by the horizontal line test and graphing, not 1 to 1. This function. This one is. This one is. And this one is. Finally, this last one. X to power 2 minus 4x plus 3. Let's see what the window is. There we go. This is not 1 to 1 because you see horizontal line test intersect at more than 1 point. So this is not 1 to 1. So again, by the horizontal line test and graphing, not 1 to 1. Okay. The last concept of the section, of the chapter, actually, is the concept of inverse function. As the name may suggest to you, inverse, well, in English language, inverse means when you undo something. Just like, you know, when you play a video and then you rewind it, or play it backward, okay? Kind of looks weird, you know. So if you think of a function that assigns to each x a unique value of y, then you can think of the inverse function as another operation that reverses that operation, takes the y and then assigns x to it. You see, that's basically a very simple concept. Something like well, if I let me go back to this picture. Actually, you see, this is a function here, right? So how do I undo this? I undo this if I reverse these arrows. You see, what happens here now, your y's are the input and x's are the output. Okay, so this is the reverse operation. You see, I'm going this way instead of going that way. So these are the input and these are the output, just like a machine. You see, you put x in there and y comes out. Now I want to do the backward. I want to put y in there. I want to see if what x comes out. You see, for the same function. So that means that if I start with y and go backward, now this y goes to two different x's. You see, this y goes back to one x. So if this is your input, then this input here has two different outputs. This input has one output. This input has two outputs. Clearly, that violates the definition of a function. So if you go backward, if I go backward this way, this backward operation is not a function for this particular function. You see? But if I do the same thing here, if I go backward, so if my function is f originally here, remember, this is not 1 to 1, this is 1 to 1. So if I reverse the operation here, you see, if I go backward, then these are my input values, these y's are the input values, and these x's will play as the output values. And clearly every input value has a unique output value. So the reverse operation in this case turns out to be a function. You see? So that's the whole idea. When you reverse an operation, what kind of operation do you have? What kind of reverse operation do you have? Is your reverse operation another function or not a function at all? It turns out, for two examples I have here, that for this one, when you do the reverse operation, reverse, I say f reverse. F reverse is not a function. Okay, but here f reverse is a function. Okay, so basically what we're going to do is this. We reverse the operations, then like a pancake, especially we turn it around and put it that way, so the input would be on the left side, and then for this one it turns out not to be a function, but this one it becomes a function. Okay, so if the reverse operation is a function, that reverse operation would be called the inverse. Okay, so if you want to have an inverse function, so you better start with a one-to-one function. Okay, so that's what we're going to do here. So that's the general idea. So because if you don't start with a one-to-one function, then the reverse operation would not be a function. So there is no point of starting with any kind of function. So why don't we just start with one-to-one functions whose reverse operation would be a function. So let me show you how we have discussed this over here. You see, you start a function y equal to f of x, let it be a one-to-one function, like this one, or like this one. This is simpler one. This is the domain of f, this is the range of f. For simplicity, I just chose 3 elements in x and 3 elements in y, or 3 elements in domain, 3 elements in range, and it's a one-to-one function. x1 goes to y1, x2 goes to y2, x3 goes to y3. One-to-one. Okay. Then we reverse the arrows. See, we reverse the arrows. Now these y's are the input, and these x's are the output. Okay. As I said before, we always want to use the letter X for input. So what we do, we just go ahead and pick this whole picture up and then flip it over. It becomes this one. You see, now this polygon shape set is on the left side and the oval one is on the right side. So that means I kind of went like this, picked it up and then flipped it over. You see, like this. Flipped it over. Just a picture. You see, I took the picture, not the whole thing. I take this picture like a pancake, flipped it over. Then these y1, y2, y3 would be on the left side, and then x1, x2, x3 on the right side. Then I change the names. I change x's to y, y to x, so x is always going to be the input value, because when you use xy plane, you see, horizontal axis is always for x-axis, horizontal axis, for that reason. So I have to change names. But if I change name, I get this operation here, and this operation is a reverse operation. And because the original function was a function, now this is clearly a function as well. So I call it the inverse function. And the inverse function, I use the symbol f to the minus 1 for the inverse function. Okay. So let's repeat this again. I start with the one-to-one function. I reverse the arrows. Okay. Then I picked up the whole picture, flip it over, and I changed letter x's to y's and letter y's to x. That would be the last product, which would be a function. Okay, let's see what this is. Let f to be a one-to-one function. The inverse of f of x, which we denote by f to the minus of y, because now y is going to be the inverse, the input, is obtained by reversing the rule of function f of x. So if x goes to y, now y goes to x. This means f to the minus 1 is the inverse of rule to f of x. Okay? But as I said, you change names. At the end, you replace x by y, y by x to get x to be always the input function. Okay? Note that for inverse function, f to the minus 1 of y, y represents the input and x is the corresponding output. So we simply interchange x and y, and we write y equal to f minus 1 of x, so that x would represent the input function again and y the corresponding output. And that enables us, that gives us the opportunity to do the graph of both f and f inverse on the same xy plane, because horizontal axis is always x and vertical axis is always y. Okay, so basically all of these sentences here, these two paragraphs, says the following. Let me summarize it. You start with the one-to-one function. To get the inverse, you reverse all the arrows, all the assignments. Here y is assigned to x, now you say x is assigned to y, backward. So I reverse the arrows, and then again I want all the x's be on the left side and y on the right side. So what you do, all the input on the left side and output on the right side. So you just picked up this picture in the middle and flip it over, and at the same time you change x's to y, y to x. You see, so now my x's are, as you can see now, this polygon shape is my domain, and this oval shape is the range. So that means the domain of f inverse is the same thing as the range of the function. You see, this is the range here. Now plays the role of So if you have your function 1 to 1, then it definitely has an inverse function. Okay, so the function has to be 1 to 1, otherwise the reverse operation will not be a function. Just like I said here, you can see one example. You have a function which is not 1 to 1. If I go ahead and reverse the operation just like this, you see, and then flip it over. Maybe I should change the shape of this domain here so that you can see the change. Let me make this one. Maybe make it this. You see, then pick it up and flip it over, you get like this one is this, and then I have y1, y2, y3, and then here I have, I'm flipping it over. You see, I just pick it up and flip it. x1, x2, x3, x4, x5. Then y1 goes, you see, y1 goes to 2 of these, y2 goes to 1, and x3, y3 goes to 2 of those. Now this is f to the minus 1, but this is not a function anymore. You see, because you are assigning to each input value to output value. But at this point, as I said, I changed this from x1 to y1 to x1, and I call this one x2, and I call this one x3, and I call this one y1, call this one y2, call this one y3, call this one y4, call this one y5. You see, now x the input, y is the output, but unfortunately this particular diagram is not a function anymore because the original function was not 1 to 1. So this is the bottom line. A non-1 to 1 function does not have an inverse function. The function has an inverse function if it is 1 to 1. So you have to start with a 1 to 1 function and then reverse the rule of assignment and then change x to y, y to x. Then what you get would be the inverse function. Okay, and that's a remark 1 here. I said the condition that f must be 1 to 1 function is essential. Otherwise, the reverse operation that we denoted by f to the minus 1 will not define a function. So only 1 to 1 functions have inverses. Okay. So if you know a function is not 1 to 1, and you just say it doesn't have any inverse. If it is 1 to 1, then you have to find it. Okay. Of course, how do I find it? Depends on how the function is given to you. If the function is given by a diagram or ordered pairs or a table, is quite easy. Okay. So let's see what it says. To find the inverse function, first we have to determine whether the function is 1 to 1. That's the first thing to check. Okay. So if the function is 1 to 1, then you say yes, it does have inverse. Then if the function is defined by the set of ordered pairs or diagram like this, if it's defined by a diagram, you just reverse the arrows, flip it over, change x to y, y to x, then you get the inverse function, just like this one. If the function is given by the set of ordered pair, then switch the position of the numbers in each pair. Like if I have, let's say if I have something like 3 and 5, then I make it 5 and 3. You see, you switch them, you flip every one of them. So if you have a bunch of order pairs, just switch each order pair, first number and second number. You just flip them over, just bang, bang, just like mini pancakes. Just boom, 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 flip them over. Now if the function is given by an algebraic equation, then to find the inverse, we start by writing y equal to f of x like this. Then I want y to be the x to be an output, Then I solve this equation for x in terms of y. You see, then solve the equation y equal to f of x for x in terms of y. After you solve it for y, then you change x to y and y to x. Interchange x and y. There's a typo here, x and y. Change x to y, y to x, and you're done. Okay. So let me clarify the whole situation by some examples here that will be clear as soon as we see the examples. Okay, here are our examples. We have these functions here. I want to find the inverse. But first of all, this is a function, otherwise it doesn't make any sense to talk about anything. But is it 1 to 1? You see, 2 is not repeated, 3 is not repeated, negative 1, 4 and negative 2 are not repeated. So yes, 1 to 1. So F inverse is just switch everything. See, 1, 2, 0, 3, 5 and negative 1, 7 and 4 and 2 and minus 2. That's the inverse function. How about this function? Is this function 1 to 1? 1 is not repeated, 2 is not repeated, 0 is not repeated, and 7 is not repeated. So yes, this is 1 to 1. So F inverse is equal to negative 2, 3, 1, 2. Oh, sorry. This is not 1 to 1. Not 1 to 1 because you see, this is not 1 to 1, so it does not have an inverse. You see, not 1 to 1 because negative 2 have two different x values, 3 and 0, they have the same y value, so not 1 to 1. Is this 1 to 1? Next example, I would say yes, yes. Check by graphing that f of x is 1 to 1. So, no doubt about that, okay? Then how do I find the inverse? As I said, start by saying that y equal to 2x minus 1, and then I'm going to solve for x, so I add 1 to both sides. These ones cancel out, I get y plus 1 equal to 2x. Then I divide both sides by 2, then these 2 cancels this 2, I get y plus 1 over 2 is equal to x. Then I change x to y, y to x. So I write this one as x plus 1 over 2 is equal to y, or usually write y first. Y equal to x plus 1 over 2, and this is the inverse function. Next one, yes, this function is 1 to 1 by graphing. So it has an inverse. So I say y equal to square root of 2x minus 1. To solve for x, I square both sides. Square both sides, you get y squared equal to 2x minus 1. Square root and squaring, it cancel out. Then I add 1 to both sides. I get these 2 cancel out. I get 2x equal to y squared plus 1. Then if you divide by 2, 2, you get 2x x equal to y squared plus 1 over 2. Now change x to y, y to x, so this implies y equal to x squared plus 1 over 2, and this is the inverse function. This one, not one-to-one by graphing. So it does not have an inverse. Okay? How about this one? This one has a restriction under its domain. You see, if I didn't have this restriction in the domain, how would the graph would look like? You know, let me just do it on the graphing calculator, and I put this restriction on it to see if it's one-to-one. You see, remember piecewise function, how we define them, how we graphed it. So I want to graph this with my graphing calculator. You see, type y1 equal to x squared minus 4, so x bigger than or equal to 0. So if you want to graph it with your graphing calculator and put this condition in, this is what you need to do. Okay, so let's do that. Maybe I should make this one a bit bigger so you can see it. X to power 2 minus 4. Then I have to go to second math, and I want x bigger than, you see, I want x bigger than or equal to 0, which is number 4. My window, I think, should be okay. Let's see what happens. Error somewhere. X squared. Oh, I forgot to put my x there. I need to put an x here. X second math number 4 bigger than 0. There we go. Now it's correct. Say graph. You see, you get that one piece, which is one-to-one. You see. If I didn't have that condition, like if I didn't have this condition, it wouldn't be one-to-one. You see? So I would say one-to-one by graphing. Actually, it looks like this. 1, 2, 3, 4. X squared minus 4 for x bigger than or equal to 0. See, the parent function x squared is moved down 4 units, and then I just consider the part. You see, actually, if I didn't have this x bigger than 0, it would look like this. You see, but I don't have this red part. Oh, sorry. This is smaller. I was saying that if I graphed it, of course, as I said, it looks like this, you see. So it's one-to-one. I graphed it here. I was saying that if I didn't have this condition x bigger than 0, if I didn't have that, then it would be like a whole thing like that. Because this is a parent function x squared, and then move down 4 units. But attaching this condition to it, that means I just want a piece that has x bigger than 0, which is one-to-one. Okay, so it has an inverse. So what I do is go ahead and say y equal to x x squared minus 4, and then I add 4 to both sides to get x squared equal to y plus 4. Then I take the square root of both sides. If I take the square root of both sides, I get x equal to plus and minus square root of y plus 4. Then, because now this is x, and x is bigger than 0, so I have to choose the positive one. Choose plus, since x is bigger than or equal to 0. So I have x equal to plus square root of y plus 4. Now I change x to y and y to x, and this is your inverse function. See? I think I am not gonna do this one here, so let's not do that. And I will not ask any problem similar to it on the homework either. Okay. One thing is, you see, like if I have this, I just draw one picture here to see what's going on. If I have a function which is 1 to 1, for the sake of discussion, let's just choose 3 elements here. See, this is 1 to 1. x1, x2, x3, y1, y2, y3. You see. Now, when I this is f, the green f. So f goes this way, and then the red is f to the minus 1. So it goes this way. You see. What does that mean? That means that if I start with f of x1, I get f of x1 right there. And then if I apply f of x1 to that, means go backward. You see, if I apply f inverse to this guy, y1, means that apply f inverse to f of x1, you go back to x1, you see. So that means that if I combine f inverse composition with f at x, then I get x back. So that's what it means. So that means if you have a function and it has inverse and you composite its the function and its inverse, it always gives you the identity. It goes back to x itself. Okay, you see, if I start with x1 by f, I go here, then by f inverse I go back to x. If I start with x2 by f, I go to y2, and then by f inverse I go back to x2. And the same thing, x3 to y3, y3 to x2. So basically what this means are the following. If I composite a function by its inverse, it doesn't matter which one I write first. F inverse composition f or f composition f inverse at x, you always end up with x in itself. Okay, that's one way to check whether two functions are inverse of each other. So this theorem is very important. Let's understand it and then see how we can do this example. It says for a one-to-one function, if a function f is 1 to 1, then f inverse composition with f is at x gives you x, and f composition with f inverse at x gives you x as well. So f inverse composition f at x is x, and so basically if you want to write it out, it means f inverse of f of x is x, and f inverse of x is also x. That's what they are. Okay. So that's one way to check whether two functions are inverse of each other, and that's exactly what this example is asking. Determine whether the given functions are inverses of each other. So what you have to do, look at f, circle f inverse at x. This is equal to f of f inverse of x. So that means in f, I replace all these x's in f by this function. Sorry, I have to look at g. I want to see if g is the inverse. So I look at f, circle g at x. This is f of g of x. You see, I want to look at these two functions. I want to see if g is f inverse. Okay, so I write f circle g or f composition g at x, which is f of g of x. So that means f of 1/2 x squared plus 3. So that means in your function f, replace this x by all of that. So it's 2 times x minus 6, but now your x is all of this expression, 1/2 x squared plus 3. Let's simplify. 2, multiply this 2 or distribute or FOIL this 2. 2 times 1/2 is 1. So you get x squared. 2 times 3 is 6 minus 6. This 6 is cancelled out. You get square root of x squared, which is just x. You see? So it worked out that way. Now if you look at the other way around, g circle f, which is g of f of x. So that means in g, replace all these x's by all this radical sign. So this is g. I said 1/2 x squared plus 3. Now this x here has to be replaced by all of this 2x minus 6 square root, like that. So if I square this square root, I get 2x minus 6 plus 3, and then distribute is 1/2. 1/2 times 2 is just 1, so you get 1x. 1/2 times 6, you get negative 3, and you have a plus 3. These two cancel out, you get x. You see? So what I did here, therefore, I checked that both f circle g and g circle f, both at x are just x itself. So that means, I can conclude, so f and g are inverses of each other. Okay. Let's go over it one more time here. I want to use this theorem to show that this f and g are inverse of each other. Okay, so I replace this f inverse by g to see if it works out. So I look at f. Let me get to this again one more time here. I look at f circle g or f composition g at x is f of g of x. The g of x is 1/2 x squared plus 3. So that means in f, which is right here, I replace this x by 1/2 x squared plus 3. So 2 times 1/2 x squared plus 3 minus 6. Then a little bit of simplification. If I distribute this 2 times 1/2 x squared is x squared. 2 times 3 is 6. And I have a negative 6. The 6 and negative 6 cancel out. You get the square root of x squared. But the square root of x squared is just x. So this part worked out nicely. Doesn't matter which one you write next. Now let's do it the other way around. G composition F. So you get G of f of x. G of f of x means G of f of x is square root of 2x minus 6. And then if I put square root of 2x minus x for x in G, which is right here, you get 1/2 all of this x squared plus 3. Square root and square cancel out, you get 2x minus 6, distribute 1/2. You get 1/2 times 2x is x, 1/2 times 6 is 3. So you get 3 minus 3, cancel out, you get x. So that means it didn't matter if I had f circle G or G circle f at x, I always got x. By this theorem, f and G are each other's inverses. Okay. The same thing here. I look at f circle G at x. This is f of G of x. F of G of x means f of 1/3 x minus 3. So that means in f, which is 3 times x plus 9, replace this x by 1/3 x minus 3. Then distribute 3. 3 times 1/3 is 1, so you get x. 3 times negative 3 is minus 9 plus 9. 9 and 9 cancel out, you get x as we expected. Let's look at G. Circle f at x. You get G of f of x. So that means I have to replace this x in G by all of this 3x plus 9. This is your f. So I get 1/3 3x plus 9 minus 3. So if I multiply this 1/3 by each one of these guys, 1/3 times 3 is 1, so you get x. 1/3 times 9, you get positive 3, and you have a negative 3. 3's cancel out, you get x. So by the theorem, f and G are inverses of each other. Okay? Okay, one more topic, and that's the graph of inverse function. So the idea is, the question actually is, if you have the graph of a function which is 1-to-1, how do you get the graph of the inverse function? Okay, this theorem says if you have a 1-to-1 function, then it has an inverse f to the -1 of x, and the graphs of these two guys are symmetric with respect to line y equal to x. So here I have a the picture I have pre-drawn for you to show you what's going on. Let's say this black curve here, this one is f of x, let's say. Okay, so this is f of x, and it's right here, you see, and it's clearly 1-to-1, so it has an inverse. Then I want to know what the graph of the inverse looks like. But according to this theorem, the first thing you do is to draw the line y equal to x, which is the identity function. This line y equal to x, bisector of the first and third quadrant, and then draw a curve which is exactly symmetric to this guy. So if you are an artist, can you draw a graph symmetric? That's fine. If you can't, one way to do it is to kind of maybe put your pencil, if you have pencil, put pencil on your graph, make it thick a little bit, and then fold your paper along y equal to x like this, and then push against the graph, and then when you open it up, you see a mark, and then thicken up the mark, and that would be the graph of F inverse. You see, so I've done this before. So if this is a function, if I fold my paper along this, you see how they coincide. You see, they coincide. So that's how the graph of a function and F inverse look like with respect to each other. Okay, and that's how you do the graph of it. The same thing here. If you have this function, the black one, you want to find the inverse of that. First of all, this function f of x is 1 to 1, and therefore it has an inverse. I don't have the equation to find the equation of the inverse, but I have the graph. I can find the graph of the inverse. So what you have to do is to fold your paper along this line and to get the inverse. But the reason this is not gonna look symmetric is because the units on x-axis and y-axis are not the same. So what you have to do is to see what point goes to what point. Like this point becomes this point, you see. So this point becomes this point. This point becomes this point, because this point is, see, is 1 and 4. So it becomes point 4 and 1. See, this point is 1, 4. This point is 4, 1. This point is 1, 0. Then it becomes, this point is 0, 1. Then it becomes 1, 0. This point is 5 and 6. You see, this point is 5 and 6. Then it becomes 6 and 5. See? And of course this point won't go anywhere. Then if this straight line becomes this straight line becomes this, and this curvy part is this one that actually I didn't do a good job. It's much better to look like this actually. Okay. And that's the inverse function. So that's how you find a graph of the inverse function if the graph of the function itself is given. Okay. So that was the last concept on section 1.6, and also the last concept of chapter 1. Watch these videos as many as you can, as many times as you want to, or you can, or you should, until you get all the concepts understood, and get to your homework problems really quickly, and be ready for your test coming up really soon.